Okay, so today now we will talk about this base station, PIFA, and terminal antennas. And these are antennas that we see in communication systems, typical cellular communication systems. So we will look a little bit first at base station antennas. Then we'll quick repetition what the price is when we try to make something smaller. And your favorite antenna, your patch antenna, is coming up there. So for example, this antenna you have built. And one thing we can see is that for a typical cellular phone, it's too big. So we will look at the version of a patch that typically is found in these kind of devices, or at least was found in them. Now it's changing a little bit the last couple of years, but PIFA antennas, which called for planar inverted F antenna, are very popular antennas in what to say constrained environments. So you can miniaturize your patch antenna, and you typically go to what's called PIFA. So we will look at that one. And in the end, we will look at some mobile phones and actually see what are in the mobile phones. And it makes it harder today because if you take a more modern cellular phone, you cannot open it. So we will go back a little bit, look at the history and actually see the antennas that sits in some of slightly older mobile phones where we can see them. And I will show pictures of a few newer ones. So if we start with base stations and base station antennas, there a typical base station looks like this. And you might have seen this base station. It is the base station that's standing on Dalbyvägen. So for example, if you're coming in with a bus from Malmö, which I basically do every day, you're passing that when you drive up Tornavägen. So this is standing next there. And there are different types of antennas. And at the moment, you know, there is a slight shift that's happening in the wireless system. So 5G is coming out. And if we look at the earlier systems, particular 2G, 3G, 4G, and so on, they are of this type that we see here. So we will look at these type of antennas. And in most cases here, you have your base station to cover some region. So you have, for example, divided here space in some set that you say, okay, this base station should take care of the users that sits inside of these regions. So you have some sectors where you should cover these users. You have divided that in size where there is very many, and maybe in more rural area where it's less people, maybe you can have less of these antennas. And you can have different versions of these ones. Like we can have one here, you can see it's some multi-beam version, and you can have some steerable beams and so on. And this adaptive version of arrays and base station arrays is really what's coming in 5G, where you should get a much more, what to say, directive radiation to the user that you would like to communicate with. And you can do this both in space and basically in time. That's what you would like to do with newer systems. I see there is one question. I'll come back to that very soon. So what we see here is then on this base station, you see different types of antennas. We will see an enlarged photo of it very soon, but you can see in many cases, you can see some elongated objects here, and you can also see some round objects that sits here. So these rounder ones are typical dish antennas, which are microwave links between base stations. So they are typically not communicating to the users. They are communicating between base stations. And the elongated structures here are really the one who's communicating to the user. And you can see now one thing, if you just think about the course, is that here you have an array. So this is these long elements that sits there. And if you just start thinking, what is the pattern? What is the typical thing that you can control this? And since it's a one-dimensional structure, it's long in this direction, but it's short in its horizontal one. It makes it quite a wide beam. But it has, in some ways, very narrow. You can control it a lot in the altitude direction. And what you would like to do typically in 5G, that's also you make them broader so you can control more dimensions in some ways. So you can also do what you say, the horizontal dimension better, which means you need an array that then would stretch out more like this, more square than this elongated structure. You get more degrees of freedom if you do that. Okay, let's see here. There comes the question how far they reach. It's very different because as you can see in this illustration here, you can see some of this is very small and you can see some are very large, and this is just a sketch. And if you are in a populated area, what you try to do is to, in some ways, have enough coverage for your users. And that means you don't want it to reach much outside of these cells. Because if you have a base station here, and if you're reaching something that sits a cell out here, so it's reaching there, then you get interference for the signals that should communicate with the users that sits in this region. So you would like actually to limit the radiation to the region of your users. And the size of this really depends on the population density. So you need enough signals in some ways for the amount of people who lives there. So if you are in Lund or you are in a big city, you go to Malmö or something, you need more dense stations than if you go to the countryside. If you go up, for example, to northern part of Sweden, I typically tend to go there. There might be one base station in every, I would say, 30, 40 kilometer. And of course, that you need then to put on a mountain or something, so it's good line of sight to many users, so it can cover a large region. And then it can reach really far. That you don't want to happen typically in a big city, because then you get interference between them. So it's very much how you design this kind of base station, how far they reach in, what you say, in the space they cover. And we don't really go into this in this course. There comes another course which is on channel modeling, which more talking about this channel between, what you say, the base station here and the user. How does the propagation work when you go from the base station to the user? There might be a direct link of this. It might hit the ground. It might hit another house that sits there. It might get reflected. And of course, then you get a different channel who goes from the base station to the users. And that's studied in those courses, not in this course. So this is what you typically would like to do with these antennas. And this is the same as you saw before. You can see this again, this small one. We will look at one of these a little bit later. You see these long ones. And as I mentioned, if you go up north, this is a place really far up north. It's above the Arctic Circle. And you can see one thing there is that the environment for this can be quite tough. So of course, if you go up north, these are actually covered in snow. They still have to work. And what that means is that what you see outside of them, for example, if you take a closer look here, you can see that the antennas is sitting inside of this gray plastic shield, and that's called a radome. It's covering the antenna. So it's trying to protect the antenna elements that sits inside of it from the environment. You need to do that coverage in some ways. And this is one, when you mentioned the distance here, this is actually an antenna standing up a mountain there. And to the next city where there is a base station, in this case is, I would say 50 kilometers. So pretty far away. And you have coverage the entire region between them, because actually you have line of sight to both of them. But then if you go further away, you don't have coverage. So there the distance can be very large between this type of base stations that sits there. And of course, the view of these can be different. Here you can see some of those point to point. You still see some typical elongated structures sitting on top of these ones. So fairly similar, but in shape slightly different, what these base stations can look like. And here is a close-up to what you can see on it again. So you typically see these ones. Next photo or two more, we will actually open it up and see what can sit inside of them. So there are many types of antennas on these towers. So on these base station towers, you put up many different types of antennas. It can be different operators, can be different frequencies, different versions, and so on that comes up there. And you just try to cover as much as you can with the antennas that you've put up. If you look at the typical base station, what sits inside of them, a little bit older version. So these are these sector antennas. here. And the typical radiation pattern is what you see there. So you can see that in the, the elevation side, it's quite narrow. So you really have a main radiation here. And that is because the majority of your users are on the ground. You don't have so many users flying up in space, so you don't need to send your radiation up there. But they are then distributed inside of this region, so you have some angle here that this base station cover. And that is due to, in these cases, you can see that it's like a one-dimensional array that sits there. So you get, in this dimension, very wide pattern, but you can get it more narrow in the altitude version. So there you can more steer a beam slightly downwards. And inside of them, there can sit different types of antennas. These are some crossed dipole that you can see up here. So you can see some feeding coming up there, and you can see some antenna elements sticking up here. So it takes both polarizations, in many cases here plus minus 45 degrees, to equalize horizontal and vertical. It means that both channels would work the same if you put them at 45 degrees. There could be patches inside of them, another type of antenna type in some ways. And then, of course, you need different frequencies because you have lower frequency band, you have higher frequency band, which means that you can put up different elements inside of these sector antennas, or you put one sector antenna for one type of frequency and put another one for another type of frequency. In newer ones usually contain different sizes in some ways. So if we open up one slightly newer one, so a sector antenna, here you can see again, it's basically one module where you can see the antenna elements if you focus in here, and you can see it more clearly here. This is very similar to the previous one with these dipoles. So you can see some feed structure in the center, and then you can see some radiation arms that coming out around these ones. And that means that you can have dual polarization that comes out from these type of antenna elements. And you can also have different sizes. So if you see these ones, they actually don't have the same size, all of the antenna elements. So quite a lot of antenna elements that sits there. But the majority of the structure is really that it's long in this direction and fairly narrow in these ones, which means that the pattern is very much controlled in elevation. So you can direct your beam, for example, downwards. You don't have to have control of all of these individual elements. You can have a pattern that goes out, and then it's quite wide in these directions. And that's because it's basically one or two elements that stands there. If you want to have more control horizontally, you would need to put more elements next to each other out here. And if you add more elements there, you would get control both in the, azimuthal angle or the elevation angle and the other angle that sits there. So both vertical and horizontal. Then you need a more square structure that comes out. So if we look at the sector antennas, they can direct the radiation in elevation part. So this long tower means you can focus the radiation down to your users, but they are not wide. So they, in some ways, ready to everybody, which is in, for example, 60-degree angle or something. So all of those users will receive the signal, which of course means that they will get an interference if they will communicate with something else, because you do radiate them. It also means you waste some energy that you transmit. It would be better if you could be really narrow beam to your user, so you don't send a signal in other directions, which means then you reduce in some ways the waste of power, but you also reduce the interference, which is a very important part, because that reduces the noise to others in some ways. And then you could use that. You can also bounce signals if you can send it more directed in different directions. So it's more efficient to have a narrow beam width. So if you can really have a narrow beam width, you can control your radiation to your users. And you can use both line of sight, you can use reflections in walls or houses. And what this means is that it requires more antenna elements. So if you think when we did arrays, we did one-dimensional array, we had control about elevation part, we didn't have control of azimuthal part. And if we need this azimuthal direction, we need to make the array more wide. We need elements both in height and in width. It could be either a flat one, it can be a round one, but you need elements there to control your radiation. And that is one thing that's been coming now in 5G and is very popular at the moment, is this massive MIMO, where you go over and actually have very large arrays. So you have many antenna elements on your base station, which means that your base station can really take care of your communication to your more simple cellular phone, and it can direct the radiation from it. You can do most of the processing up there. You don't need to have as many elements in your cellular phone, and it can then direct the radiation to you. If it's line of sight, send just one beam to that one. If you have another house, send one beam to the user and send one to the house and get reflected in the house, and then end up from a different direction to the user. You can either use it to increase the signal strength, or you can send 2 bit streams to it. One message that way and basically one message this way. And then of course it's combined, so not separate. You just increase the number of bits you can send. So you can simultaneously here really steer the beam in almost any direction. And then you can utilize what this multipath is, that you don't need line of sight. If it bounces in something, let it bounce. If you want some illustration, there is a lot of course YouTube videos and so on. Here's one link that sits here that try to illustrate both the spatial part and the timing part of this. So you could think about this. It's one way of using it would be similar to time reversal. If it takes longer time to bounce in the wall, just send that signal a little bit before, and after a while it will end up at the same time at your source or your user as the line of source. And you can actually control that with this kind of massive MIMO systems. You will study the MIMO in other courses. Here in Lund, there's been a big research topic, and I'm pretty sure you have seen it before. So one of this very first test beds for this is the one that you can see here. So here you see a large array. It's a patch array, dual polarized patches, typically with 100 ports. It can have different configurations, but you can have 100 signals. And you can also see this can basically be used in 2 settings. One way is to say that you use this centerpiece. And if you think you have this centerpiece, you have basically a square array, which means that you would have the same control and elevation here as you have in azimuth. If you instead use it in the opposite or the longer version, for example, that sits there, then you would have an array which is more wide in this direction and more limited in the elevation part. And then you can, of course, get different beams out of these ones, how you put them in. So you can test different things. And you can see one thing that is for 3.7 gigahertz. You can see this is huge. The system that sits there. Huge electronics, very, very heavy, very, very big. Nowadays, it's coming up higher frequencies. So in 5G, you want to go to millimeter waves, or around 30 gigahertz. And this is a similar thing, which is a cylindrical structure instead, that you can see here with, again, a patch array. And now it's put on a cylindrical structure, so you actually can cover every region around it. And you still get a good control of the radiated signals that comes out. You don't have in each direction maybe as many as you have here, but instead you have coverage all around it. And again, a lot of antenna ports. And here you can see one of the great advantages of going to millimeter waves, and that's that the physical size goes down. So these are physically smaller structures because the frequency is higher, so the wavelength is shorter, which means that the antenna elements are shorter in some ways. And then, of course, you need to do a lot of processing and so on, and that electronics, of course, takes its size also. So that can be done in different ways. But this is an antenna test system for that. So that is what we have in base stations. And a good thing with base stations is that at least until now, they have not been limited in size. So there have been rather few problems of, for example, putting up these kind of towers that we can see here. I mean, you have your tower is big. The antenna elements is not what really is super big inside of it. It starts to change when we go to Massive MIMO, and especially Massive MIMO at lower frequencies, because then you would actually need something that is quite wide here. And that can actually be problematic to put up on these towers. It, for example, would increase the wind pressure on them quite a lot, which could be an issue that comes in. We don't really know at the moment. But so far, it's not been a huge issue. But of course, when you go to the terminal side, so you go to these ones, it's completely different because you have to cover your terminal antennas. You have to cover your cellular phone. You don't carry the base station. So the pressure to make something small is much, much higher on the terminals than it is on the base stations. And we looked a little bit at the last lecture, what is happening when we make something small. And what we saw there is that when you shrink something, you always pay a price. And the typical price you pay is determined by this number here, which is called the Shu bound, which says that you can take Ka, so the electrical size of your structure, the radius that sits around it. So for example, if you have a cylinder structure here, you put some sphere around your object that is radius A, and then you take K, 2 pi over lambda, and you take that quotient, and if that quotient is big, your Q here goes up. And if your Q goes up, you go narrowband. And if you sit in a cellular system, you cannot live with Qs that is, for example, 100. That would talk about a few percent in bandwidth. You need a lot of bandwidth. So you need to have basically low Q systems in some ways. They don't need to be ultra wideband, but they should be wideband. So it's really an issue here when you start shrinking things. And we know pretty well how this is happening for different geometries. If you have another geometry, you can, for example, see in these rectangular cases here, you can get some value. This is a scale version of directivity in Q that says that every rectangle sits below this ones. So we know we pay a price for this. And that's, of course, we have to do inside of these devices. We make them smaller because they need to be smaller. We have to pay a price. And we have to, of course, make good antennas that sits there. And if we look at the terminal side, we can really see that we pay a fairly high price in some ways. So a modern type or slightly modern type phone, you have a few percentage on the side to make your antennas. Maybe you can make it on the top, you can add a little bit on the sides and so on, but it's very, very limited that space you can use. And the rest is basically a screen, so it's close to a perfectly electric conductor. And that means that your Q here will be high. So on a typical size here of 600 megahertz, yeah, you can go down here and you get fairly high Q values if you don't do something that is better in some ways. So it is a challenge in some ways to get these small antennas into these devices. So we will look a little bit at what is actually done in these kind of cellular phones to get these antennas inside of them, because you need to have many antennas inside of your cellular phone. And we will start with one thing that comes from your patch antenna. So your favorite antenna, I mean, you all designed your patch antenna. Half of you had also measured the radiation patterns of you, and rest will do it in January. So you know quite a lot about your patch antenna. And what's really the fundamental understanding of your patch antenna comes from this cavity model. And in that one, we got out that we had a typical length, which is half a wavelength in the substrate of the patch. So it means it's half a wavelength size. And that means that it's not a small antenna. A patch antenna is actually quite big. This is not electrically small. Half a wavelength, everything is fine. It's quite electrically large. So it won't really do it for our cellular phones when we need to really shrink the size of them. But a good thing with them is that they occupy a very low profile. So that is the part that you have with the patch here. In this case, it's very thin. So even if it's wide here, if you have a structure, a hull of something, you can actually put patches there without making the structure much larger. So that you can make them conformally basically to the structure that sits there. And to analyze them, we used this cavity model where we had an idea here that this is how the electric and magnetic fields look like below the patch. And then comes the question here. If now this patch is too big, so size is too big, I mean, this is 2.4 gigahertz. Say you would like to make this at 600 megahertz, then you have to take the quotient between 2.4 and 6. So that's basically a factor of 4. And that means this is 4 times larger. So your patch will be big, 4 times these dimensions. Very, very large structure in some ways. So at least how can you make it slightly smaller? How can you shrink the size of your patch? So we need to do something. And if you just look at what you have in these cases, do you see some obvious way you could actually at least reduce it a factor of 2? That's actually the start to the antennas that basically sits in all older types of cellular phones, internal antennas. That will give us our PIFA antenna, which is in some ways a modified version of half a patch. And they're modified, I would say, in 2 steps from the patch. So if we think again about this, okay, we know we have the cavity model. And what does the cavity model here say? It says here that the electric field behaves as sine pi x over L. L is the dimension that we have here, the length dimension. What does that mean? It means that if you go to the center of this patch, along a line here, along that line, the electric field here is 0. Because that's in the center of it. And if you remember of your patch antenna, if you put the feed in the center, it doesn't really work. And that is this electric field that is 0. Your radiation resistance goes to 0 at this center point. So you cannot feed it in the center. But can you do something else if your electric field is 0 at the center? If the field is 0, what happens if you put another object in there? So if the electric field is 0, if you put in a metal, the requirement is that the tangential component of the electric field has to be 0 on the metal. That really means I can put a metal wall there. So what you can do in the center of these ones is that you can actually put a metal wall here. It doesn't change the cavity model because the electric field is still 0 on that metallic piece that sits there. So here I put a metallic wall. And if I put a metallic wall here, I have a feed on this side. That means delete what sits on the back side. I can just take it away because now this metallic wall shield the field from that side. So all the field is on the side where I feed it. And if there is no field there, let's take away the top part too. And suddenly you made your patch half the size. That is the first step to actually make this kind of what's called PIFA antenna, planar inverted F antenna, which is very much what sits in these miniaturized versions. Many, many types of those antennas sits there. So if we look at this PIFA antenna, that is what's in some ways comes in modifications of cellular phone antennas, especially the slightly older one that was a little bit thicker. So this is the antenna in that picture there. And one thing you can see of them is that if you see the height, now I don't have a super thin phone, but you can see this one is much thicker. You can of course see if you see the side of that, yes, it's much smaller. So it's smaller in size, screen of course ridiculous, and thickness is quite high. And nowadays when we make them smaller, it makes it even harder to make the antennas, and I will show you how to change them in a different direction. So when we look at these antennas, we would like to have some kind of low profile antenna. And what we can in some ways adjust is the metal that sits here. So if you see a model for this or this type of antenna, you can see it here. So you can see in these cases, here is some feed of it, here's some short circuit, and you can get some currents there, but you also get a lot of currents on this ground. And you try to make everything resonant in these cases. So if we see then what's happening with this PIFA, so that is I would say, half a rectangular patch antenna. So what we do is precisely what I mentioned before, is that you take your patch, you have your feed here, and then you basically short circuit one side of it. Then we do the first step of modifying our patch. So it's half a patch. And it's the basic start of this PIFA antenna. And PIFA stands for planar inverted F antenna. So it can be considered as this rectangular patch with a short circuited side. And a modification that's also often used in these cases is that you don't short circuit all of this. Maybe you only short circuit a part of it. And then you go to some modifications, which is similar to what we see in these phones. So a picture of it would be the same as here. Let's consider from the beginning that we could think about this basically as an infinite ground. On a finite ground, in most cases, you actually end the ground plane on the edge, which you have short circuited, which means then you have some feed point somewhere, you have a short circuit side or only a small fraction of it, and you have half a patch that sits above. And in the first order, this means that it would be as half of our patch antenna. That's what we have there. So if we look at it, we have our cavity model. So the model of the cavity. And as I just said before, in the center of it here, the electric field is 0. So there the electric field is 0. And if we then put a metal wall there instead, we can actually just plug in or we can remove half of it. So the patch is half a wavelength in the substrate. And then we just throw half of it away. And that means that the PFAS length is half of the patch antenna's length. So the L are different for this PFA. It's half of the patch. And that means it's quarter of a wavelength than half of the wavelengths to get the resonance in the PFA compared to the patch. So for the same frequency, it has then half the size. So that's really where you can put it in. And the reason is precisely as I mentioned before, that we can put this PEC surface here to short circuit this side here. Because the electric field is already 0. And if the electric field is 0, yeah, let's put the metal wall there. And then you can remove the back side of it. So the bottom part here, you basically just take away. And you only keep the front part of it. So you keep half of your patch. And if we look at the typical radiation, so this is simulations of PFA antenna. So you can see the geometry, you can see a feed point sits there, you can see this side in this case is short circuited. So it's really half a patch in this cases. It has short circuited along all the side. If you look at the field underneath it, precisely half of the patch. If you now remember back to lecture 5, there we show this pumping cavity field under your patch. So plus on one side, minus on the other side, pumping up and down. Now it's only one of them. Pumping up and down. We took away half of it. If we look at the field above it, we can see very strong fields here on the edges. And really the strongest one is the one that sits here. And that is what dominates the radiation that comes out. So the radiation of this antenna should be as radiation from one dipole, one magnetic dipole. So we can approximate the radiation from one magnetic dipole. And it's one magnetic dipole above a ground plane. What is the directivity of a typical dipole? It's 1.5. It sits above a ground plane, which means directivity goes up to 3. You double it because you don't radiate below it. And if you can see here, it's typically what you can see in these cases. So values in these cases fairly close to 3 for this type of really infinite ground plane type of PFA antenna as it is here. And if you look at the pattern of it, you can see it's a 0 in this direction. And now can you imagine if you just complete this around here, what do you see then? Yeah, that is your donut pattern of your dipole. So you're taking your donut and you cut half of it in the opposite version as if you would, I shouldn't say you should eat it, of course, but think about a bagel or something. You cut it that way, you don't cut it that way. And that is the shape that you get out of this type of half patch type of antenna. And that is the simplified part of the radiation. That of course we have very strong electric fields on this side, so very strong here. And that means that we can model these ones with a magnetic current that goes there. So here you have your JM. And here, very weak fields and very weak fields there. So everything is dominated by this field that sits along this width side of this that dominates the radiation. These currents also have opposite direction. So for example, in the normal direction, they cancel each other, which means that the radiation is pretty much as the radiation from one dipole instead of the patch, where it was two dipoles separated in space. And that increased the directivity of your patch. And the radiation pattern, you know very well the radiation pattern of a Hertzian dipole. And of course, that's an electric current. Now it's a magnetic current. So you have to change your electric field to a magnetic field. So it means that in these cases, the polarization of this one will be that the H fields in the normal direction is as directed as this dominant magnetic current. And that means that your electric field is as for the patch instead in this direction. It's in the X-directed version of this when you go straight up. Same as if you would have a patch in these cases. Then you get other effects. You get cross polarizations and so on, which comes from these type of currents there. But if you want any higher details of that, we have to go to basically full wave simulations. But the basic understanding you can get from a simple understanding, from a simple model, and that gives you the understanding of the radiation patterns. Then when it's put on a finite ground plane, it starts changing because then it depends on the size of the ground plane. So yeah, again, here is the radiation pattern, and here we can see half of your donut type pattern, or this 8 pattern in some ways. So one dipole in this case that is directed like this. And then it is above the ground plane, so you take away the lower part, which then doubles the directivity when you go up. That is the radiation pattern that we have, which is quite easy to understand and actually see what that radiation pattern is. So that is one version to come up to this PIFA, where we start with the patch antenna. Sometimes this antenna I had now calls just a half a patch antenna. And we don't really distinguish those in these cases. An alternative way of doing that, which actually motivates the name here, this PIFA, planar inverted F antenna, is to take the move to this antenna from a monopole instead, where you go from a monopole to what's called an inverted L antenna to an inverted F antenna to a PIFA. So you go there in steps in some ways. So if you start thinking about your monopole, so you have a ground plane here. So this is PEC here, PEC that sits there. And then you have this monopole sticking up, and you know that L here is basically lambda over 4. So your monopole sticks up a quarter of a wavelength from the ground plane. And you know that the radiation from this monopole is, of course, like this. So it radiates along the ground. There is a 0 radiating straight up. That is what you have in your monopole. And then you could think about, okay, let's modify this. It's sticking up too much. What do I do? Yeah, remove this top part here and just bend it on the side here. It would change stuff. It would change the radiation, but probably you can make that resonant. So let's do that as a first step. And by just breaking this monopole and then putting it along the side, you get what's called an inverted L antenna. And if you think about the name, just think about the shape of this one. It looks like an L. So that's why that one is called an inverted L antenna. So there you have your inverted L antenna. You took your monopole and you just bend it. And of course, things change a lot when that happens. I mean, the length with the resonances are changing, the impedance is changing, everything is changing in some ways. But you make it go to height L, which now can be much less than L. So you put it down there. So now it is long along the ground plane, but it doesn't stick up that much anymore. That's your inverted L antenna. And then, of course, just think about the name. What is then an inverted F antenna? If this is an L, so here you have your L, now you should have an F. What is an F? You have to add one more pin that goes down. Then you get an F instead. So that is where you get an inverted F antenna. And then you can ask which one should be fed and one should be short-circuited. And in most cases here, this is the fed elements as it's there. So that means that what we do from the L antenna is that we add a piece of this one that goes out and short-circuited to the ground. You add a short circuit to it. And then we will have our F antenna. So here we now have our F antenna. So here is our F. And that is now the inverted F antenna. And then in the next step, we go to what's called the planar inverted F antenna. And then you start thinking, okay, what did we learn from the dipoles? What did we learn about bandwidth and dipoles? And also for your patch and bandwidth. How did you increase the bandwidth of your patch antenna? What did it have to do with? You had a length and you had a width. And your bandwidth was related to the width. The same when you had your dipole, if the dipole is a very thin wire, you can increase the bandwidth by making it wider. Fat is good. So you make a fat antenna. And that you also do with this PIFA. So you take these ones and you actually stretch it out here above the ground. So you make it into the plane of this. You make it wider. You make it fatter in some ways. And then it's a planar structure above the ground plane, which looks precisely as what we had before, which was this patch to PIFA antenna. So we can come to this antenna in two different ways, basically equivalent ways. It's easier probably for us to understand the function when we come from the patch antenna and the cavity model. The name comes more natural when we think about this monopole, L to F, okay, planar wide, and that's the PIFA antenna. And when we do that, we can also see that, of course, I don't have to short circuit everything here and feed it everywhere. I can just pick some points, and I can start playing with the geometries. So you improve the bandwidth by using a thick structure. And now what I mean with thick is into the screen where you see it. So you make it wider there. Then you increase the bandwidth. And that gives then the planar inverted F antenna, which is the PIFA. That is the PIFA antenna. And then if you would like to reduce size, then you can start thinking, okay, what did we do with a monopole or a dipole? And if we had these ones first, one thing you were doing was like something like this. You try to just shrink it down in length. And of course, that means if you have this one, you can also try to make it a little bit longer there. And the same thing now, if you have this one, you can then maybe add some slots or something that makes the current takes a longer path. Then you can shrink the size. And that's actually what we see typically in these devices. We will take a look at them after the break. So that is a PIFA antenna. So further improvements of this is to do precisely what I mentioned, that you can change the geometry. And the first thing is typically this, that we don't use a short circuit of everything here. So if we say here, you have a feed structure here and you have a short over there. So we don't short the entire side of it. And you don't put these ones in these cases over an infinite ground plane. This is really a finite ground plane. And the size of this ground plane here is of the order, typically maybe lambda over 2 or less. So it's really a structure in these cases that we cannot in any way consider infinite. And of course, in these cases here, when you're behind it, there is nothing. So when you think about the model from monopole, inverted L, there the thinking is really like infinite kind of structure. But when you use it, of course, here it's finite. So we use the same thinking anyway. And then, yeah, the placement and the shape of the finite ground plane comes in. In most cases, if you think a phone, you're not allowed to change the size of the shape and size of the ground plane. It is what it is. You cannot do much about it because the screen is important. But you can shape the patch. And what you can see up here, which come back to these ones, are typically these patches. These are modified to have dual resonances, because in this kind of phone, you need a 900 band and an 1900 band. So you need 2 resonances on the same patch. Nowadays, you need many more. And you can change them then cutting away pieces here. So in these cases, you have one dimensions there, and you have a longer dimension there. The longer the dimension, the lower the frequency. So you can start playing with that, which means that one way of looking of that is that you cut away some slots that sits here. So you take away some piece of the metal, which forces the current to go around it, taking a longer path. So that can improve the performance further. And you see the same thing here. You can go like this part of the current. And that's a longer path due to this slot where we have removed a piece of the metal. And when you do that, of course, everything that we learned with the cavity model and so on doesn't work anymore. It's too modified. But the basic ideas can still be related to it. And then in reality, of course, you have to combine it with things that you build inside of the phones and so on. And there are various different techniques used to actually do this for multiple resonances. And I will show you some of them after the break. We will come back to those cases. So that means that we will, after the break, see how these are actually used in some cellular phones. So we take a look at see what sits in some phones, what sits in them that's coming now, what's happening with 5G and millimeter waves and so on. But that we will do after the break. So now it's time for a break. So I will stop the